Water molecules often go through a process called dissociation. We can use this illustration to show what happens in that process. If you focus on the bonds between the water molecules, you'll notice that some bonds break down while new bonds form, and this gives rise to two new molecules. One of them, the hydronium ion, and the other is the hydroxide ion. Now this process can happen in both directions. The forward direction that I just showed you, but also the reverse direction, where the hydronium and hydroxide give rise to water. The equation shown here is what actually happens. It takes two water molecules to give rise to the hydronium and the hydroxide. But conventionally, we'll show it in this way, as one water molecule giving rise to a proton and a hydroxide. Now what's important here is that the proton shown in the bottom equation never actually exists by itself, but it always exists as a hydronium ion. But throughout the remainder of this presentation and in most books, you'll talk about proton concentration and not hydronium ion concentration. So it's just important to remember that. In pure water, the concentration of protons and hydroxide ions is equal, each of them at 1 × 10⁻⁷ molar. So the product of these two is 1 × 10⁻14 molar. When you're not dealing with pure water, these concentrations tend to fluctuate, but they fluctuate together. If you have an increase in one, you have a decrease in the other. Say the proton concentration goes up, then our hydroxide concentration will have to go down because the product of these two always has to be 1 × 10⁻14 molar. So if our proton concentration goes up to 10⁻⁶, then our hydroxide concentration has to go down to 10⁻⁸, and that trend will continue. And the opposite would be true as well. If hydroxide concentration goes up, then proton concentration would have to go down. The concentrations of protons and hydroxides brings us to the concept of acids and bases. If you add an acid to a solution, the proton concentration will increase and the hydroxide concentration will decrease, whereas bases have the opposite effect. If you add a base to a solution, proton concentration will go down and hydroxide concentration will go up. We'll focus first on the acids. If you add hydrochloric acid to a solution, this will cause an increase in proton concentration and a decrease in hydroxide concentration. The way this happens is that when hydrochloric acid is put into solution, it dissociates into a proton and chloride ion. These protons are what increase the proton ion concentration. Now you also decrease hydroxide ion concentration. You do this by combining hydroxide with the protons, and they form water. This lowers the hydroxide ion concentration. Bases will have the opposite effect. If you add sodium hydroxide to a solution, you will decrease the proton concentration and increase the hydroxide concentration. The way this happens is that when you put sodium hydroxide into solution, it dissociates into sodium and hydroxide ions. These hydroxide ions give rise to the increase in hydroxide concentration, but they also decrease the proton concentration. Protons will combine with the hydroxide and form water molecules. This will lower the proton concentration. When dealing with acids and bases, you have both strong and weak acids and bases. The difference is that strong acids completely dissociate when you put them into solution. This will provide a more drastic effect on the proton concentration, whereas weak acids and weak bases do not dissociate completely, so they don't provide as many protons or hydroxide ions and don't cause as much of a change.